I am going to introduce now random variables. A random variable is a function x from a sample space S into the real numbers. We are going to write our v as a short for random variable. Usually we use capital letters, capital X, capital Y, for example, to denote random variables. If we have many variables, then we can use subscripts with capital letters. For example, capital X1, capital Y1, capital Y2, and so on, to denote random variables. We are going to use lowercase letters, lowercase x, lowercase y, or we can also use subscripts on them to denote the values of the corresponding variables. A discrete random variable is a random variable x with a finite or countably infinite set of values, which can be viewed as a list: x1, x2, x3, ... So when I say that x is a discrete random variable, it simply means the values of x can be expressed as a finite list or as an infinite list. Let's look at an example. Let's say we are flipping 3 fair coins, and if we flip 3 fair coins, what's the sample space? Well, we can obtain the sample space by making a tree diagram. So if I am flipping 3 coins, then from the first flip I can get a head, or a tail, and let's say from the first flip I get a head. If I get a head from the first flip, then from the second flip I can again get a head or a tail, and whatever I get in the second flip, then again I can get a head or a tail from the second flip. Similarly, if I get a tail from the first flip, then I can get a head or a tail from the second flip. If I get a head from the second flip, then I can get a head or a tail from the third flip again. Similarly here. So I can read off the results from the 3 flips by reading the nodes in my tree diagram. So I can, for example, get head, 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 or head, head, tail. I can get head, tail, head, or I can get head, tail, tail, and so on. So I can read all the results, and also I know how many results I should be getting, how many outcomes I should be getting, because there are 2 possible outcomes from the first flip, there are 2 possible outcomes from the second flip, there are 2 possible outcomes from the third flip. So there is a total of 8 possible outcomes from the 3 flips. So if I flip 3 fair coins, then I get 8 possible outcomes, because I'm assuming the coins that are fair. all the outcomes are equally, all of the 8 outcomes are equally likely. Let X denote the number of heads. If X denotes the number of heads in 3 flips, then the possible possible values of X are 0, 1, 2, or 3. Now here X is a function from the sample space into the real numbers. So let's express X as a table. So in the first column I have all the outcomes, and the outcomes are denoted by omega here. And then in the second column I have the value of X for that outcome omega. So if the outcome is HHH, well, then the number of heads is 3, so X would be 3. If the outcome is HHT, then the number of heads is 2, so X would be 2. And if the outcome is THT, then the number of heads is 1, and so the value of X is 1 here. And if the outcome is TTT, then the number of heads is 0 and X is 0. Okay, so X is a random variable which is a function from the sample space into the real numbers. Okay, now when we write X equal to 0, what do we mean? When we write X equals to 0, we mean the event that 0 heads occur. And so X equals to 0 denotes the event consisting of outcomes S in S such that X of S is 0. And so the event X equals to 0 consists of only one outcome, TTT. So what's the probability that X is 0? Well, the probability that X is 0 is the same as the probability that the probability of getting 3 tails, and which is the same as 1/8, because we assumed that the coins were fair, and therefore the outcomes in the sample space are equally likely, and this event has 1 outcome out of 8 possible outcomes, so it is 1/8. So here in the following table I have each value of X and the corresponding events for those values of X, and in the third column I have the corresponding probabilities. So when X is 0, the corresponding event is TTT, and the probability that X is 0 is 1/8. If X is 1, then the corresponding event is the event of getting 1 head out of from 3 flips. So the event is TTH, THT, HTT, and the probability that X is 1 then is 3 out of 8. If X is 2, then the corresponding event is the event that we get 2 heads in 3 flips. So the event is given by HHT, THT, THH, which is 3/8 again. And if X is 3, then the corresponding event is the event of getting 3 heads from 3 flips, which consists of only one element, HHH, which is and the probability that X is 3 is 1/8. Notice that if I add up the probabilities, I should be getting 1. And because the values from 0 to 3, they exhaust all possible values of X. Okay, so now let's say I want to find the probability that X is greater than or equal to 2. The probability that x is greater than or equal to 2. Okay, so the probability that x is greater than or equal to 2 is the same as the probability that x is 2, or x is 3. And so this would be equal to the probability of the event that x is 2 union the event that x is 3. The probability of the event that x is 2, more loosely we just write p of x equals to 2 without the without the curly brackets. The probability that x is 3 and the probability that x is 2 is 3/8. Sorry, there is a typo that I made here, so this will be a plus. The reason is the event that x is 2 and the event that x is 3 are disjoint, so I can add the probabilities, and this will be 3/8, which together gives me 6/8. And oh, sorry, the probability that x is 3 is 1/8. Again, I am basically getting those values from the above table. The probability that x is 3 is 1/8, x is 2 is 3/8, which is going to give me a half. If I want to find the probability that x is larger or equal to 0, that's the same as the probability of the union of the events x is equal to I, where I is 0 to 3, and that's the same as the sum I going from 0 to 3 of the probability that x is equal to I. So this is the sum of the probabilities of the values of x, and that's 1, which we saw in the table. The sum of the probabilities of all the values of x is 1. Now I keep writing the probability of x greater than or equal to 1, and I'm writing x greater than or equal to 1 in parentheses, but it's probably better to write this probability of x greater than or equal to 1 and putting curly braces around x greater than or equal to 1, because usually we denote events by using curly braces, so it may be sometimes confusing if we don't write those braces, but I usually wouldn't be writing the braces, so keep that in mind. Okay, so I'm going to take a pause here. Alright, so some of the notations that I have to mention here. When we write the p of x equals to x, what we mean is the probability of the event consisting of all outcomes omega in the sample space for which the value of x is equal to x. When we write p of x greater than or equal to x, what we mean is the probability of the event consisting of all outcomes omega inside of S for which the x value is greater than or equal to the lowercase x. And similarly for probability that x is less than or equal to x, if we have two variables x and y, and if we write the probability of x equal to y, what we mean is the probability of the event consisting of all outcomes omega inside of the sample space for which x of omega is the same as y of omega. If we write the probability of absolute value of x minus 2 is less than or equal to 1, what we mean is the probability of the event consisting of outcomes omega in the sample space for which absolute value of x of omega minus 2 is less than or equal to 1. Okay, so I'm going to pause here, and what you need to do is read this the statement of this problem, and we will solve this problem.